we started with how networks affect our lives, and we started by defining what is a node, what is a computer, what is a network, the different types of networks. Maybe I will record the same so that I can share for those who missed. But in our very first class, we started by understanding how do networks affect our lives. And then after understanding how they affect our lives and how we can use them, we came down to the different components in the network where we were talking about the end nodes, the servers, the clients. That is part of the first lecture. But then when we came to the second one is where now we started looking at the network models, which now I want us to look at and address a little bit. Now, when we are talking about a network model, it is all about how the design of the network is put out or how the design of communication is laid out. Because for communication to take place, then some things have to be there. Even in the first lecture, there is something that we said governs communication. Different people are going to talk with one another. And when they are communicating with one another, they have to agree on how they are going to communicate. If today I started communicating with people, then I use a language that is not understood by those people, then communication will not be efficient or it will not be successful. So when communication is taking place, there are things we call protocols. Those are the rules which are going to govern that communication. And in that first lecture, which I will also refer to, but here I'm looking at it so that at least we have an understanding of where we are coming from and now where we are going. But we will also look at it in a little bit. So for that communication to take place, there is going to be what we call a protocol. We normally say a protocol is a rule. Just revising a little bit, we said for those communications to take place, there is going to be a protocol. And a protocol, we said it is a rule that will govern communication. So it determines how or it determines what is being communicated, how it is communicated, and when it is communicated. So I hope, Korea, we are together up to there. Okay, so at least you will be able to look at this. So those three things, that is why we were talking about synchronization and all of that. The key elements will be the syntax, the semantics, and timing. Those are the key elements we will find in any protocol or any rules. So when we are talking about syntax, we are looking at the structure or format of the data. That is what is involved in syntax, whereby you need to show how to read the bits. That is, what is the structure of that data. So that is the first aspect of any communication protocol where we are talking about the syntax. Like I was saying, if I was to communicate and I am not using English or Swahili, language that is understood by everybody, and I use another language, it will be very difficult for somebody to know the meaning of what I am saying. It could be important, but if there is no rule governing how we are communicating, then we have a problem. So that is why Protocols are very important. The other one is semantics. And when we are looking at semantics, we are looking at the interpretation of the meaning of the bits. So there has to be a way when I say this, what does it mean? Or how is it going to be interpreted? That is what it means. And then timing deals with when data should be sent, and then at what speed, it should be sent, it should be sent or received. So once you have established those guidelines or the rules of communication, then it becomes very easy to have this model or the design of communication whereby we use the concept of layers. And here an example is given, two friends who are communicating through the postmail, although nowadays it is not there, through poster. Then the process of sending a letter will look something like this. The sender is going to write a letter, put it in an envelope, and then drop it into the mailbox. Then the letter is carried from the mailbox to the post office. Then the letter is delivered by the carrier of the post office to the next post office. Once it has been delivered from the carrier to the post office, this is at the receiver side. Maybe you're sending a letter from Nairobi to Mombasa. So in from Nairobi, from your estate, then it goes to the post office. Then from the post office, it is taken through the highway to Mombasa. At the Mombasa post office, it is there. Then from the post office to your mailbox. Then from your mailbox to your home, where you receive it, you open the letter, and you're able to read it. So this is the same model that we try to use, or that has been put into use for us to understand how communication can be designed using networks. And this is established through the ISO, International Standards Organization, which was established in 1947. That is when the ISO standard was established. But it has different kinds of standards. The one that we are interested in is the Open Systems Interconnection, the OSI. This OSI was first introduced in 1970s, and its work is to bring about the concept of communication, or to model or to design how communication can take place in networks. If you look at the 1970s, through the history of networks and internet, this is the time now networks are being used in a commercial way. Initially, networks started with the Department of Defense in the US, whereby they were trying to have communication between different military camps. That is the main concept about networks and communication at a distance, or what we call telecommunication. Telecommunication refers to communication at a distance. It started in the 1940s through the Department of Defense, whereby the US had different military camps, and for them to communicate, they needed to have the model of signaling. So you go to that history, you can see how signaling started using the Morse code. Then it came down to the signals themselves now being packaged and being able to be transmitted over distance where there is no cable. It is wireless transmission through the radio systems. And so it also came down to research institutions or universities, University of California. When we start looking at the different encoding methods, that is where we realize there were those encoding methods used by the military, there were encoding methods used by universities to exchange communications and to be able to carry out research with one another when they are at at a distance. The University of California and many other universities. Then now in the 1970s is when now people realize we can do communications in a commercial way. People need to communicate. People are still testing the ideas of having mobile phones or telephones, which were being used then. So the OSI model was established. It has those 7 layers. And these 7 layers are the ones that have been now used to ensure that communication takes place. So we have the application. So we normally name them from the bottom. So layer 1 is going to be physical layer. Layer 2 is the data link layer. 3 is the network layer. 4 is the transport layer. We have the session layer. We have the presentation. And at the top, we have the application layer. So the purpose here is to look at each one of them and what it does. So let us move. When we are talking about the interaction between the different layers of the OSI model, then we have, let's say for example, there is this device which needs to communicate with device B. And in the middle, there are intermediate nodes. It said that in our previous class that when you see this X, it means that that is a router. When you see the one with 2 arrows pointing in different directions, that is normally a switch. But we will see that when we are doing the practicals. So just to tell you, these are routers, which are the intermediate devices. So this device will prepare a message. Let's say it is an HTTP message, maybe on Gmail, HTML. Gmail prepares a message and it wants to send. So Gmail will communicate with another Gmail application on the other side. What does that mean? The application that has been used to prepare the message here is the same application that will be used to open the message on this side. It's like when you are chatting on maybe what is it called? Facebook Messenger or on WhatsApp. You can't send a message on WhatsApp and it is opened using another application. It will only be opened with a WhatsApp application. If it is the Facebook Messenger, the same will be used on this other side. That is why we are talking about those two kinds of communication, where we are talking about same layer interaction. When we were talking about the adjacent layer interactions, now this layer prepares the message for transmission. You type your message, you attach your photo, and that's it. You move it down to the adjacent layer, which is presentation. And then this one does its own business there and moves it to the session, which does the same business. And then you go down to transport that way until you get to the physical layer where transmission takes place. In these 3 layers, we are talking about what we call node-to-node transmission, although this is end-to-end. Because here, the ones which are painted yellow, something will be happening. The source address here will be for this device. The destination address will be for the next intermediate device. As the data frame moves from this device, the source will be this intermediate device to this other one, but only at the third layer where the address, which is logical, remains the same. That is also something else we shall be looking at just to see the different types of addresses that are normally used. We said that at this layer here at the top, we normally use what we call these 3 layers when they are combined in the TCP/IP model. They normally use what we call the normal addresses. Here we use the port addresses. Here we use logical addresses. Here we use the MAC address. So that is the different types of addresses. We shall look at them. So that is the interaction between the layers. So this IP address or the logical address remains the same during transmission, but the MAC address keeps on changing as the data frame is moved from one host to the next until you get to the destination. So what helps for this data frame or the data packet to be moved from source to the destination is the logical address. Because when this device receives this data frame, it will check in the encapsulation and check which is the destination IP address. Yes, I have received this data frame, but inside the data frame, there is a packet. That is why the encapsulation takes place. Here, it was just the data. Down here, it became what? A segment where we attached the TCP address. Here, it became a packet where we attached what? The IP address or the logical address. Here, it becomes a data frame where we attach the MAC address, which we are saying it keeps on changing. So when this device looks at the data link layer, it will check and see that I am not the destination IP address, so it will forward that data frame to the next node. It checks again, it is not the destination and forwards until you get to the destination IP address. Then now the other activities can take place. So if it was some kind of peer-to-peer connection, like here where we are doing the circuit connection of establishing a link which can help us to communicate, then TCP kicks in after this packet has been received. So after it has been de-encapsulated at the destination IP address, then you find that what is required is a connection to be established. Then now TCP kicks in for the connection to be established and other things can now take over. If it was just a message to be read later, then TCP forwards it or moves it to the next adjacent layer, whereby now the synchronization can kick in and the encryption and decompression takes place, and you are able to see the message that has been sent. So that is how the layers are going to interact with one another, either as adjacent layers or as different or same layer interactions. I hope we have no question up to there. Then we move on to the physical layer, which we start with. And we say the physical layer is responsible for the movement of individual bits from one node or hop to the next. So like we were showing in that diagram, when you are receiving a data frame from the data link layer, it is going to be converted into individual bits at the physical layer. And these are the bits that will be either converted into electric signals, because at the physical layer, if you are using the cable as your transmission medium, then it has the bits have to be encoded into electric current. If we are using wireless, then they have to be converted into analog signals for transmission. And that will be something we shall be looking at in a while. So at the physical layer, that is where we are talking about these bits being moved from one node to another. Then we continue to the data link layer, which is layer 2 of the OSI model. And we say that the data link layer is responsible for moving data frames. So at the physical layer where encoding takes place, here is where we are talking about encoding, whereby if it is one bit, you are saying, because the computer understands the language of ones and zeros. So we are saying a bit may be converted, and let's say we are using the cable for transmission. So one bit will be converted to maybe, and we normally use the direct current. So we are talking about voltage levels of 5 volts or no volts. So one bit can be converted by using different encoding schemes like the return to zero, or Manchester encoding schemes. Those are things we shall look at. Although for CCNA, not so important. For the networking classes, we normally teach those. So for CCNA, we are talking about converting 1 bit into maybe an electric current flowing, a 0 bit, no current flowing. So once you do that encoding, that is attaching meaning to these bits, then they are transmitted on the physical medium. But as they were coming from the data link layer, they were data frames. And the data link layer is responsible for moving the frames from one hop to the next. And so, like we said, a frame is going to be an encapsulated data which contains the TCP, it contains the IP, it contains the MAC address. So the work of the data link layer is to read the source MAC address and the destination MAC address, as well as perform error checking, because it has a trailer which does what? It does error checking. Why does it need to do the error checking? Because as the bit was being moved through the physical medium, let's say it was a cable, and somehow it has been affected by maybe attenuation, where the signal has lost strength, it is moving, then it needs regeneration. Or through the wireless, where there was some kind of noise. Sometimes even the cable, let's say you have put your cable in a trunk where there is also cables transmitting electricity. Sometimes, and there is a power surge. Then the normal transmission on your data cable may be affected, whereby a bit was a 0, it is converted to a 1. So that is an error. So the FCS, the frame check sequence, is supposed to check for those errors. So that is what is happening at the second layer. It receives data frame from the network layer. It attaches the MAC address and the frame check sequence. Then it moves it down to the physical layer. The physical layer moves that data through the medium. Then at the receiver end, it gives the data frame to the data link layer. The data link layer will check through the use of the MAC address. It is able to receive the data frame, and then it does the error checking. So if you want to see the hop-to-hop delivery, this is how it looks like. An end system here is going to prepare a message for transmission, and then it does move it through this link to the intermediate system. This intermediate system is going to check. Since we have these two end systems, and our intended recipient is node F, not node D. So this one is going to check, maybe the intermediate system is a switch, and it checks the MAC address, and it sees that the destination MAC address is on this side. So it will not forward the packet or the data frame to this route, but it will take this route and deliver it. So that is how hop-to-hop delivery is done, or node-to-node delivery is carried out in these two layers. Hope up to there we are all together. So the network layer is the third layer, and on the third layer, we are talking about delivering individual packets from source host to destination host. So notice here, the other one we were doing hop to hop, whereby this address, the MAC address keeps on changing as you move from one device to the next. But now, when we have come to the network layer, something else kicks in, whereby we are saying that the data packet, now we are not calling it frame, it becomes a data packet. So the packet is supposed to be moved from source to destination. That is where the logical address comes into play, the IP address, because the IP address will remain the same from the source to the destination. Only the MAC address keeps on changing. So once data is received from the transport layer, it comes to the network layer where you attach the IP address and then forward it to the data link layer. It moves through those intermediate nodes until it reaches the destination through the help of the IP address. Once it reaches there, now it can be de-encapsulated. This is what we are talking about. So as you are moving from source to destination, these two, you can see that they are divided, meaning that the destination address here becomes the source address as you move to the next hop. But this color here, blue, shows that the IP address remains the same. That is why we are talking about source to destination delivery, not hop to hop delivery. So down here, we are talking about hop to hop delivery, but at this layer, we are talking about the IP address remaining the same from the source to the destination. Then we come to the transport layer. And at the transport layer, we are talking about now doing delivery of message from one process to the other. Like we were saying, different applications are going to communicate with one another. For instance, for us here to be able to communicate, we are using WebEx. WebEx is an application that is helping us to communicate. And so the source address or the source process is this one which I'm using to transfer this message to you as the destination nodes. So when this data is received from the session layer, what happens? The TCP protocol is attached so that when the message reaches the destination or when the packet reaches the destination and it has been seen as to be interpreted for a connection orientation, then that connection orientation is established so that the WebEx application on this machine can be able to communicate with the WebEx application on the recipient machines, which are for you as the students. So that is what is happening at the transport layer, which is shown here. This application or this process, because an application will be broken down into different processes. That is how a program is normally executed by the CPU. So those processes are the ones which are communicating. So at the network layer, we are talking about host to host delivery, whereby the purpose is just to get the maybe the packet from this machine to this machine over the internet. But once this message reaches the machine, that is not the end. What else? The message has to be interpreted, and that interpretation is taking place at the process level or at the application level, whereby now the program which is intended for interpreting interprets it, and once it has interpreted it, then this communication will take place. So we get to the session layer where we are saying it is responsible for dialogue control and synchronization. So what do we mean by dialogue control and synchronization? That is where now the preamble of the data frame comes in, whereby now you have to synchronize or establish what transmission speeds are being used and how do we manage this dialogue control. Like I have said, somebody could be transmitting, maybe the network I'm using, the transmission is at 100 megabits per second. But the receiver or the person who is receiving this message is at a lower speed, 10 megabits per second. So you need to do synchronization. One of the methods which is used for synchronization is buffering, whereby at the receiver router, that message is going to be collected there so that your machine, which is receiving at a lower speed, can now receive from there bits by bits. So buffering is one of the methods, and it can work in both ways, whereby again, if the transmitting device is transmitting at a lower speed, like for example, you are watching a video on YouTube and your connection is not so good. Sometimes you normally see that cycle where it tells you, please wait, buffering. What is happening? The immediate router is trying to collect enough video or enough multimedia information so that it can be delivered to your device. Because maybe your device is receiving at a higher speed or at a lower speed, but your network is a bit slow or is a bit fast. So buffering can take place where you are trying to receive the entire video and then deliver it bits by bits. or receive the video bits by bits and then deliver the package as a whole to the receiver. That is what we talk about synchronization or dialogue control. At the presentation layer, that is where translation, compression, and encryption of data takes place. So when information is received from the application layer, after you have created your WhatsApp message, it will be brought to the presentation layer whereby it is translated. Remember, at the application layer and all these three layers, that is application, presentation, and session, they are taking place at your device, meaning that it is your computer processor or your smartphone processor which is responsible for these activities. So the message which you are preparing in the normal English language, maybe on Gmail. Once you prepare it, the computer understands the language of bits, and so that is a language of zeros and ones. So translation will be converting the normal English language into the machine language which is used by computers, which is zeros and ones. So that is how translation takes place. Then after translation has taken place, compression takes place. That message has to be compressed. It could be like 5 MB or 10 MB. But for us to ensure that network resources are properly utilized, then compression takes place, brought down to maybe 10 kilobits, 100 kilobits. And then encryption, that is putting it into a format that cannot be decrypted or cannot be read by an interception during transmission. So once that has happened, then it can be forwarded to the lower layers. At the receiving side, when it reaches the presentation layer, the opposite takes place, whereby you have to translate, you have to decrypt. Once you decrypt, you uncompress, and then you translate that message for it to be given back to the to the application layer. That is where we get to the application layer, whereby here you are working with applications that are using protocols like maybe HTTP, which is normally used by YouTube, Gmail, and all of those. Any web browser is going to use HTTP. So when you're using HTTP, then that is the human language or the user language, which we as users can understand. And that is how we can get services from these systems. So that is prepared and then passed down to the presentation layer for all those other activities. When it comes back to the receiver, then the opposite takes place. After the translation has happened, then you're going to use the same protocols, HTTP or whichever, FTP, whichever protocol, so that you can be able to read the message that has been brought back. So those are the layers and how they normally work. So here is the summary, whereby we say that the application layer is supposed to provide services or network services to the user. Presentation layer is responsible for translation, encryption, and compression of data. Session layer is supposed to establish, manage, and terminate sessions. Transport layer is reliable for process-to-process communication or message delivery and error recovery. The network layer is responsible for moving packets from source to destination so that networking can be provided. The data link layer is supposed to organize bits into frames and provide hop-to-hop delivery. And then the physical layer is supposed to transmit the bits over the medium, or it provides the mechanical and electrical specifications. So that is the OSI model on which we base the TCP/IP protocol suite. The TCP/IP is the actual implementation of how the OSI is used, or what is now put into use in the commercial application is the TCP/IP model, whereby it is going to combine the first three layers are going to be combined into one. In the TCP/IP model, they become the application layer. Transport remains transport. Internet or the network layer remains network layer or the internet layer. These two are going to be combined into the link layer, although need to note to give you a caution here. In some areas, the two are going to be divided. The data link layer and the physical layer are going to be divided into two when you are using the cabled network. When you are using the wireless network, they are combined together to be the link layer. And we are saying the protocols which are used here, they are defined by the underlying networks. Whether you are using the Ethernet network, you're using the token ring network or the architecture. So the underlying network architecture, how you are physically connecting devices, is what is going to determine the protocols which are going to be used in the physical and data link layer. But in the network layer, we have the IP protocol as the main one, and then we have these others, which we shall see. When we are talking about ARP, it refers to Address Resolution Protocol. It is supposed to countercheck the different addresses and they are and their corresponding domain names. The reverse address resolution protocol does the opposite. When you are given a domain name, then you convert it to the specific IP address. The IGMP, the Internet Gateway Management Protocol, and the ICMP, the Internet Control Message Protocol, we will also look at them. The transport layer, we normally use the TCP, but then we also have the UDP and the SCTP protocols, which we shall also look at. And then at the application layer, we have these many HTTP for any web browser. Simple Mail Transfer Protocol is for the sending of emails, and then the File Transfer Protocol, the DNS, the SNMP, the Telnet. Those are the protocols which operate for different applications, which are at the application layer. So that is how they are normally laid out. Now, how does addressing take place? We normally have 4 levels of addresses when we are in the TCP/IP model, whereby we have the physical, the logical, the port, and the specific addresses. So how do they work? At the application layer, we normally have the specific addresses. These are addresses like your Gmail address, your Gmail email address. That is a specific address. We also have maybe the domain name addresses like www.spu.se.ke. That is a specific address. But then we come to the transport layer where we use port addresses. So any application that has the capability to communicate over the network or over the internet, it will always have a port address. And some of these are configured automatically when you have such an application installed on your computer or your smartphone. So when you talk of like Simple Mail Transfer Protocol, or the mailing protocol, you will find that port 21 is going to be there automatically. So those port addresses are there by default. When you go to Google too, and then you try to look at them, you will find all of them, they are listed there for different applications. So those ones are just automatic. They are 16-bit addresses which are normally used for different applications. Like for example, if I could just share this, just a simple Google search will give you some of these port addresses. I hope you can see them. Like the FTP, File Transfer Protocol, it will have port number 20. Another FTP will also have port number 21. The first one is for data transfer. The other one is command control. SSH, secure shell, which is also for data transfer but in a secure mechanism, is port number 22. Telnet is port number 23. Simple Mail Transfer Protocol is port number 25. and this is for email delivery. So whenever you're using any email, Yahoo, Gmail, whatever, it is going to work with port number 25. 53 is for DNS. 67 and 68 is used for DHCP. Whenever you go to a place where there is Wi-Fi, and then you uh, save that Wi-Fi account in your mobile device, you leave and you come back, automatically you will be connected to that Wi-Fi. How is that done? Through the use of dynamic host configuration protocol. And so it means that since you have the DHCP application on your smartphone, so port 67 or port 68 has been configured for assigning you an IP automatically. Then HTTP, which is used for browsing the internet, is using port number 80. Port number 110 is for Post Office Protocol, POP3, although it is not so popular nowadays because we have gone to SMTP. POP3 was used in previous emails, like those people who were using Outlook, or the other one was called what? I can't remember, but mostly Outlook. So if you are using Outlook, it is based on POP3. So port number 110 is used for that. Network News Transfer Protocol is port number 119. 123 is for the Network Time Protocol, Internet Message Access Protocol, or the IMAP, which is used for digital mail management, is port number 143. 161 is for Simple Network Management Protocol. This is for where now different routers or intermediate devices are supposed to communicate with one another in terms of notifying each other if one of the intermediate devices has gone down or it has an issue or there are new routes which have been found. All of that is done by the Simple Network Management Protocol. Then there is the Internet Relay Chat, the HTTP, Secure, and DHCP for IP version 6. So those are different, and they keep on growing as the applications are growing. So that is something you will realize as the applications which have the capability to communicate over the internet grow, then the network the port addresses will keep on growing. So that is what we mean by different port addresses. Then logical addresses, these are the IP addresses. And any device that is going to communicate on the internet or is going to operate on the internet has to be given a unique identifier, which we call the IP address or the logical address. Why? It is because at the physical layer, like we have said, there are different underlying networks or different network architectures. Somebody can create a network architecture based on Ethernet. Another person can create a local area network based on maybe tokenry. So those are different network architectures, and the addresses in those network architectures are going to be different, the MAC addresses and all of that. So in order to avoid that confusion of the different network architectures, that is why we came up with the logical addresses, so that whenever these devices want to communicate globally, they are able to communicate. But for local communication, we normally use the MAC addresses, which are based on the local area network architecture design. Like we have said, even the topologies are going to be different. You find that one network has been designed using the star topology, which is very common. Another network can be designed using the bus topology. Another local area network is designed using maybe the mesh topology and so on. So those different physical architectures are going to be common for that particular local area network. But for the devices in that local area network to communicate globally, then they will require the logical addresses or the unique identifiers we call the IP address. So the physical address is the MAC address, which we have said that it is a 48-bit address that is divided into two. The first 24 bits are going to be the OUI, or the organizationally unique identifier, which is for the maker of that device, and the other one is for the device identification. The logical address is a 32-bit address, whereby it is 4 octets of 8 bits which have been assigned. The port address is normally 16 bits. And then the specific addresses, like we have said, they are the ones we know in the human language. Maybe it is the domain name, it is your email address, and so on. So that is how we have those ones organized. Any question up to there? Any question? Okay, so if we do not have any question, let us do a summary of that, the Cisco presentation. Whereby it talks about the protocols and the models, some of which we have already dealt with. So we will just skim through this one very quickly just to understand. So here it covers the rules, whereby you're going to describe the types of rules that are necessary for successful communication, the protocols, why the protocols are necessary in network communication that we have done, then the protocol suites, that is, how do you adhere to a protocol suite, and then the standards, organizations, the standards that are responsible for establishing the protocols for network interoperability. Then we also have the reference models, which we have said we have the TCP/IP and the OSI model, and how they facilitate standardization in the communication process. Then we have data encapsulation, how data is encapsulated as it is transported across the network, and then data access, how local hosts are going to access local resources on a network. This is very important because it is the one talking about the physical layer. So the first thing we need to understand is how protocols are going to help us in facilitating interoperability, and this we start with the rules. And so the rules are going to show us, or any communication is going to help us understand that there, for it to be complete, there will be the source or the sender, there will be the receiver, who is the destination, and there will be the channel, which is the medium that provides a path for the communications to occur. So that is how communication is going to take place. So here we are going to have the communication protocols allowing us to communicate by governing how communication takes place. And then the protocols are going to vary depending on how communication is taking place. So for example, we are going to have the message where it is coming from the source, then it is translated into a signal by a transmitter, and then it goes through the transmission medium, then a receiver gets the signal and then it translates it back to the message. So it could be two people. So if it is two people, what happens? It is going to be, maybe they are speaking in the same language. You hear what the person is saying, then you interpret it in your mind and you are able now to communicate back. Then if it is an email, it is coming from this device here, it is converted into a signal that goes through the medium, and then gets to the receiver. So that is how it is going to work. So this is what is explained here, whereby we are saying that human communication is going to be governed by rules. So you need to understand how the message is brought and how it is going to be used. But these rules are going to operate differently. Though they have the similar concept, but they are going to operate differently in computer-based systems. So protocols have to make sure the following has happened. One, there is going to be a sender and a receiver. So that is the work of a protocol, making sure that there is an identified sender and there is an identified receiver. That is where we have the source and destination address. Then there is going to be a common language and grammar, what we were talking about in terms of syntax and semantics. Then the speed and timing of delivery is very important, which we talked about in terms of timing. At what speed are you sending, and the timing of the delivery of that message. And then some protocols like those in the transport layer, they are going to ensure there is confirmation or acknowledgement of recipient. That is why we say that TCP is going to be connection oriented, meaning that once the message has been sent, it will ensure that it has received the message, and then it gives what we call a feedback or an acknowledgement that the message has been received, it has been properly interpreted. Compare that to the IP. The IP, it just ensures that the message has been sent, but it doesn't have the reliability of giving an acknowledgement. So that is the difference between the two. So when we are looking there at the network requirements in terms of protocol establishment, it means that the message needs to be encoded, meaning that because the user or the human being will understand the normal English language, or the computer is using the bit language, the binary language, then the message needs to be encoded into the language of transmission. Then the message formatting and encapsulation has to be there, like we have seen the different items that are added into the message as it is being encapsulated from one level to the other. Then the message size has also to be there, the message timing has to be there, the delivery options have to be there in any protocol. So this is what we are talking about here. The message has to be encoded, it has to be transmitted, the medium the channel is going to use is also specified, and so on. So when we are talking about message formatting and encapsulation, we are saying that when it is being sent, it has to be in a specific format or structure. The message formats depend on the type of message and the channel that is used to deliver the message. So if we are talking, for example, in the normal human communication, we are talking about a letter. So it means that the letter has to go to the post office, and then it goes through, it is transported to the destination post office. Compare that to an SMS. An SMS has to be prepared on your mobile phone, then it is sent through the phone service provider, and then it gets to the recipient. So even if there are two people sitting next to one another, still the SMS will take that same channel, going to the service provider and then coming back. So that is how we are talking about a message being prepared. Now, this is what is explained here. That SMS will contain the destination address and the source address. Then it will have the length, the header, and maybe the hop limit. How many hops does it need to go through? And then the flow control mechanism, as well as the traffic class and the version. This we will look at when we are looking at the datagram itself. Then we move on to the message size. When we are talking about encoding, then we are saying that we have to have some kind of appropriate format for the medium to use, so that when messages are being sent on the network, they will have to be converted into bits. The bits are going to be encoded into a pattern of light, depending on what we are using. If we are using fiber optic cable, then we are talking of light. If we are talking about multimedia transmission, then there will be sound. If we are talking about cabled networks, then we are talking about electrical impulses, so that the destination host is able to decode those signals and interpret the message. So that is what we are talking about, the sizing and the kind of encoding and decoding that will take place. So when we are talking about message timing, which is also part of the protocol, then we are saying that it has to include the following. One is flow control, whereby it is going to manage the rate of data transmission and define how much information can be sent and the speed at which it can be sent. Like we have said, if your device is transmitting at 10 megabits per second, but the receiving device is receiving at 100 megabits per second, then there has to be some kind of flow control, where we have said the basic mechanism which is normally used is buffering, so that you can ensure both are receiving at the same rate. Then there is response timeout. How long a device is going to wait, and when it does not hear a reply from the destination, then it is going to give a feedback that there wasn't communication. Like we have said, there is always an acknowledgement. After the receiver or the destination has received a message, it has to give an acknowledgement that it has received. If it doesn't give an acknowledgement, maybe after a specific duration of time, there is going to be a timeout. And maybe one of the methods we use is the ping command. You can ping a particular destination, like the practical we are doing. If the message has not been received or there is no acknowledgement of received, you will see a timeout, maybe after a specific duration of time. And then the access method. This is going to determine when some message can be sent. And there may be various rules which are going to govern. Of course, the access methods, like we shall see, there is what we call contention mechanisms. The medium that we are using is the same, and many devices want to transmit through that medium. And so we need to manage things like collisions, because if two devices are going to send at the same time, they might collide, or the messages are going to collide because they are using the same message. And when collision occurs, the messages are going to become corrupt. That is something we need to access. That is why we have different access methods. Some protocols are going to be active and they are going to prevent collisions. That is why we have protocols that have access mechanisms attached to them, so that wherever there is a collision, or if a collision has not been prevented, then they can be able to establish a recovery mechanism after the collision occurs. So when message timing is going to be included in a protocol, flow control has to be there, response timer has to be there, and the access method has to be there. How are the messages going to be delivered? Messages can be delivered either as unicast, that is one-to-one communication, or as multicast, where we have one-to-many. Like here, we are using an multicast method, whereby messages are coming from this machine, but to a specified recipient. Think of it in the sense that nowadays we are using the subscription. This is a pay TV, whereby if you pay for something like Go TV and you pay for this package, you will receive those specific channels. Somebody who has not paid, as much as the signals are available, they are not able to receive them. But then there is broadcast. Think of KBC, whereby as long as your device is able to receive that signal, then you will be able to get it and you can be able to see the transmission that is taking place. So that is how messages can be delivered, either as unicast or multicast or as broadcast. So broadcasts are used in IP version 4 networks. That is something you need to understand, but they are not an option for IP version 6, and we will see why that is the case. And also, that is where we include things like anycast. Instead of broadcast, we have anycast as the option for IP version 6, and we will get there when we come to IP version 4 addressing and IP version 6 addressing. So here we are just using the different types of connections using these different nodes. So when we are talking about one-to-one is from this node to this specific, that is unicast. Multicast, it is coming here, but to these specific ones. When we are talking about broadcast, is to all of them. So it is just using the graphical representation. Then we get to the protocols. And protocols define a common set of rules and they can be implemented in devices either as hardware or software or both. And each protocol is going to have its own function, it is going to have its own format, and it is going to have its own set of rules. So a protocol which is used in network communications is going to enable two or more devices to communicate over one or more networks. If a protocol is used in network security, it is going to secure the data, that is by providing authentication, by providing data integrity, and by providing data encryption. Those are the protocols which are used for security. There are other protocols which are used for routing, and these ones are going to enable routers to exchange route information, compare path information, and select the best path. That is one of the functions we said for routers. Routers are supposed to check the network performance by determining which is the best path, and best path is determined by using number of hops and network congestion. Then we have service discovery. There are protocols which are used for discovering services available on the network, and those ones are for automatic detection of devices on the network or services available on the network. Like we have said, if you go to a place and you scan for the Wi-Fi, so you are using a protocol that is enabling you discover maybe the network service. So that protocol is for that purpose, and we will get to those. So the network protocol functions, we have said they are for devices to agree upon how they communicate, and they may have one or more functions. So you could find protocols that are for addressing, and those ones are supposed to identify the sender and the receiver, that is like the IP. Others are for reliability, and these ones are used to provide guaranteed delivery, like the TCP. Others are for flow control, and they ensure that data flows at an efficient rate. And we will see also TCP and SCTP are also used for that purpose. So some may have several functions, may have one or several. Others are for sequencing, that is uniquely labeling each transmitted segment of data. Like we have said, that is for frame management. Uh, Unique labeling is done at the data link layer, and we will see the different protocols because they vary from the different architecture of the network which is being used in place. There is others which are used for error detection. They determine if the data has become corrupted during transmission. That is also like frame check sequence, where we are talking of cyclic redundancy check and so on. That is found also in layer 2 and also in the fourth layer, which is transport layer. Then there are others which are for application interface, which enable processes to communicate with one another between different network applications. So those are the network functions you will find with protocols. Then, how do protocols interact? So networks will require several protocols for them to interact or for communication to take place. And each protocol is going to have its own function and its own format. So how do we ensure that there is that kind of interaction? Like here we can see on different layers of the TCP/IP, we are having different protocols that are ensuring that this mail is going to be moved from this device here through the internet to the destination device. So it will contain the HTTP, the TCP, the IP, and the Ethernet protocol so that it can be able to move. So when you look at the hypertext transfer protocol, which is the HTTP, it is going to govern the way a web server and a web client interact, and it is also going to define the content and format. That is where we have said, if it is a web server, any web browser is going to use HTTP. That HTTP is the one which is going to show the kind of format that is being used to display information, and the kind of content that is displayed on that web page. Then TCP, Transmission Control Protocol, is going to manage the individual conversations. It is also going to provide guaranteed delivery, and it is also going to manage flow control. Like we have said, here we have established a connection using TCP, of course, and since that connection is established, then we have to ensure that the individual conversation, if somebody tried to chat to me, it is TCP that is going to ensure that individual conversations are going to be established and they are going to be managed properly. It is also going to provide guaranteed delivery. Like right now, anybody can be able to hear me, and there is also a flow control because different devices might be transmitting or receiving at different data rates. Then flow control is managed by the TCP protocol on each of those devices. Because my device has the TCP, your device is going to have the TCP protocol, and it is going to perform those functions. Then IP protocol is going to be used to deliver messages globally from the sender to the receiver. So this one is supposed to ensure that any device that is going to receive that message, it doesn't matter, it is a message to be read later, or it is a message that needs a connection to be established, like the one we are doing now. For that message to move from this sender to the receivers, then it has to use the IP protocol. Any device to receive that message needs to have the IP, or the unique identifier. Then Ethernet at the bottom here, the one which is going to be found at the physical and the data link layer, is going to be used to deliver messages from one unique card to the next on the same Ethernet or the same local area network. So if we are on the same local area network, then it is Ethernet that is going to work, or it is the physical or the MAC addresses which are going to operate. And here it is how it is working. As much as we are on the same local area network, we are using an application we're calling WebEx. So the message is going to be converted, or it is going to be encapsulated into a data frame, and then it will move from this NIC card of my machine to the NIC card of the nearby switch. Then the nearby switch transfers it to the next hop, which is a switch, and then to a router, and then the router is going to move it to the web or to the internetwork, and then it gets back to the same channel at the receiver end, which would be your machine, and it is converted on by the higher level protocols. So that is how that message can move from this machine to the intended recipient that way. Then let us look at the different protocol suites, the ones we had looked at. And a protocol suite is a group of interrelated protocols that is going to perform a communication function. Those set of rules are going to work together to help solve a problem, such that you may not have one specific protocol, but you need several protocols that are going to work together. And these protocols can be viewed in terms of layers. We have the higher layer protocols and the lower layer protocols. Higher layers are used for preparing the messages, like we have said, the HTTP, the FTP, those ones which are used at the application layer. But there are these other lower layer protocols which are concerned with moving data and providing services to the upper layers. Those are the ones we will basically be dealing with mostly. So here they are, the different protocol suites. And the most common one that we have is the TCP/IP protocol suite. That is why it is called the TCP/IP model, because it is the most common and it is maintained by the Internet Engineering Task Force, the IETF. And you will see that at the application layer, it has things like HTTP, DNS, DHCP, and FTP. In the ISO model, it has those. In AppleTalk, it has the AFP. In Novell NetWare, it has the NDS. we will concentrate for the Cisco networking class, we will concentrate on the TCP/IP. When you come to the transport layer, we have the TCP and the UDP. That is what we will concentrate on. Not that there are no others, the others are there. On the internet layer, we will concentrate with IP version 4, IP version 6, ICMP4, and ICMP6. On the network access or the link layer, we will concentrate with Ethernet, ARP, and wireless LAN because that is what we commonly use. Then we also have another suite which is the OSI. We also have the Apple Talk, which is a proprietary suite by Apple. We also have Novell Netware developed by Novell Inc. So an example of the TCP/IP suite, this is how it works like we had explained, so that you will find you will need to have Ethernet, the IP, the TCP, and HTTP to be able to move this email message from your machine to the web server, and it goes to the destination and comes back as a response. So that is how the construction is made. The TCP/IP, that is how it is going to work. So the TCP/IP is an open standard that is freely available to the public, and the standards-based protocol is endorsed by the networking industry and approved. That is why any device manufacturer will put into consideration the TCP/IP protocol stack so that their devices can work like that. So how is the TCP/IP communication process established? So you will find that a web server is encapsulating and sending a web page to a client. How does it do that? It does that by, first of all, it starts from the application layer where you have the user data. Then the user data is going to be brought down, or is going to be broken down into different TCP segments, and the TCP protocol is attached. Then after that, it is broken down into packets, and the IP addresses are attached to the packets. And then after that, it becomes an Ethernet frame, which is now going to move at the physical layer. So that is the communication between the web server and the web client. So how is this happening? At the Ethernet level or at the physical layer, it is going to be converted into a series of zeros and ones, which are going to be encoded for them to be moved. But you will need all of these. The user data, which is in HTTP, is broken down into TCP segments and then broken down into packets, whereby you attach the IP addresses, and then the Ethernet frame where you have the MAC addresses and frame check sequence. So that is how the message is going to be moved. The client will receive that web page for the web browser, and they will start by encapsulating. So it is the reverse of what has happened. So they will start with a series of zeros and ones, then they will go to the frame, to the packet, to the segment, until you get to the user data. Then the standards and the organizations, we have different of them. And the reason why we have the standards is to encourage interoperability, meaning that any manufacturer of these networking components, be it the network interface card for the computer, be it the switch, be it the access point, be it the router, all of those are going to be manufactured by different manufacturers. But the goal is to ensure that there is interoperability. The devices can operate with one another. It also encourages competition so that the best one can be used. That is why you will find that many devices are Cisco based. Why? Because they are competitive. They are creating devices that are over the edge, and there is innovation, meaning that different manufacturers are going to be innovative in the kind of devices they are going to create, such that they are better in terms of operating. And so standards organizations are going to be vendor neutral. That is why you can use a Cisco device together with a D-Link device, together with maybe an Apple device because they are vendor neutral. The standard is going to cut across those different vendors, and they are also non-profit organizations. So talk of IEEE, ITF, IANA, ITU, ICANN, TIA, all of these are different organizations which are coming up with these different protocols and standards, but they are non-profit organizations and they are vendor neutral. The reason why they have been established is to develop and promote the concept of open standards, standards that can be adhered to by different device manufacturers. So we have the Internet Society that promotes the open development and evolution of the Internet. We have the Internet Architecture Board, IAB, which is responsible for management and development of Internet standards. The Internet Engineering Task Force that develops, updates, and maintains the Internet and TCP/IP technologies. So if you have an innovative solution or an innovative algorithm on the TCP/IP protocols, on any of the TCP/IP protocols, then the organization you need to deal with is the Internet Engineering Task Force. And something which I had forgotten to mention is that in the TCP/IP development, or the reason why we have those different layers, because somebody could ask, why do we have those layers? One of the reasons is that you can be able to advance or you can be able to modify one of the layers without affecting the other layers. That is where the aspect of innovation and improvement comes in, or updating. You could go and develop another protocol for the transport layer, and it will still work with the other layers without any challenge. So that is why we have the different layers, such that there is what we call, what is this term? Once I remember it, I will tell you. But you need to have that kind of separation so that whatever you do in one layer may not affect the other layers. Then we have the Internet Research Task Force, IRTF, which is focused on long-term research related to TCP/IP protocols. So these internet standards, or the organizations involved in development and support of TCP/IP, are also going to be governed by these two bodies: the Internet Corporation for Assigned Names and Numbers, that is the one which coordinates the IP address allocation, the management of domain names, and alignment of other information. Also, the Internet Assigned Numbers Authority, which is going to oversee and manage IP address allocation, domain name management, and protocol identifiers for ICANN. So all of these other organizations are going to be governed by these two bodies. Then the communication standards are going to be found with the IEEE, which is Institute of Electrical and Electronic Engineers. It is dedicated to creating standards in power and energy and healthcare, telecommunications, and networking. We have the Electronic Industries Alliance, which is dealing with developing standards related to electrical wiring and connectors. This is very important because of the physical layer. Don't wonder why we are talking about electrical wiring and connectors. At the physical layer, we are going to be dealing with purely electric current and voltages, and the connectors which are going to be used for the communication, as well as the racks, which are used for mounting networking equipment. So here, imagine after you have connected all your devices and they are going to a switch somewhere, they are going to find a rack or a terminator cabinet, which is going to be created by the Electronic Industries Alliances. The Telecommunication Industry Association develops communication standards in radio equipment. So again, at the physical layer, for wireless communication, you will find the TIA, which is going to develop standards for radio equipment, cellular towers, voice over IP devices, as well as satellite communications. Then we have the International Telecommunications Union and Telecommunications Standardization Sector, which is going to define standards for video compression, Internet Protocol Television, IPTV, and broadband communications such as digital subscriber lines. So those different standards are going to work at those levels. So up to there, at least we have understood the different standards and the different bodies which are normally used for coming up with those open uh, standard models. Then the reference standards, we already looked at this, that is the OSI and the TCP/IP and what they normally do. So the benefits why we have the layered model is that you can assign or it assists in protocol design, because protocols that operate at a specific layer have defined information that they can act upon and a defined interface to the layers above or below. They also foster competition because products from different vendors can work together. They also prevent technology or capability changing in one layer affecting the other layers above or below. That is why we have the layering of these models, and then they provide a common language to describe networking functions and capabilities. So we have those ones. You can look at them. We had already looked at all of these layers where we talked about application layer, talking about process-to-process communications, whereby different applications are going to operate at that layer. We also have presentation layer, where we are talking about common representation, where we are talking about now translation. That is where common representation comes in. Then presentation layer is going to manage the data exchange, that is through synchronization and timing. Transport layer is going to provide the segment transfer and reassemble of data for individual communications. Network layer, it provides services to exchange the individual pieces of data over the network. The data link layer describes the methods for exchanging data frames over a common media. And then the physical layer is going to provide the means to activate, maintain, and deactivate physical connections. So this is just a repetition of what we had done. That is a TCP/IP reference model. You can look at it. And so this is how they are going to compare with one another, the TCP/IP and the OSI model. Then we have the packet tracer. This is now the simulation which we use in Cisco, and it is intended to provide a foundation for understanding the TCP/IP suite and the relationship it has to the OSI model. And the simulation mode will allow us to view the data contents being sent across the network at each layer. So that is what we will be doing with packet tracer when we should be using it. When we are talking about data encapsulation, how is data encapsulated? So segmentation is going to take place at the transport layer. And it is the process. When we talk about segmenting message, it's the process of breaking up messages into smaller units, and this enables multiplexing. Multiplexing is the process of taking multiple streams of segmented data and interleaving them together. So segmenting has two primary benefits. It is going to increase the speeds because smaller bits of the uh, message are easier to transmit on the network. So large amounts of data can be sent over the network without tying up the communication link. And it also increases efficiency in that only segments which fail to reach the destination can be retransmitted and not the entire data stream. So that is why we are doing segmentation at the fourth layer, so that we can break down the message into smaller units and then ensure that we can multiplex it, or we are going to take those multiple streams of segmented data and interleave them. Interleave ni kama vile unaona one message stream or one segment is following the other. So it's like we have broken down the message into different segments and they follow one another. That will increase the speed and improve the efficiency. Then we have sequencing. Sequencing is where the messages is the segmented messages are going to be numbered so that the message can be reassembled at the destination. So if you have a message broken down into like 10 segments, you're going to number them 0 to 9, and then when they reach the destination, despite where they went through the network, they are going to be reassembled following those sequence numbers. Then after that, when you have broken it down, normally it is a data unit as it leaves the application layer. Here it is a data unit. But at the transport layer, you are going to make it a segment. So at each stage of the process, the protocol data unit has different name that is reflecting to its new function. So here we are going to name it according to the protocols of the TCP/IP suite, where you will start with the data stream, that is the application layer. Then at the transport layer, it becomes a segment. At the network layer, where we are adding these headers, the transport header is the TCP. The network header is what? Is the IP. And now it becomes a packet. At the data link layer, we have the frame header, network header, and the transport header. Here, the frame header is the MAC address. The network header is the IP address. The transport header is the TCP, then the data, and then we have a frame trailer, where we have said that the frame trailer is the frame check sequence, the FCS, which is supposed to check for errors when the data was being transmitted. So the frame check sequence is also attached as a trailer. And then at the physical layer is where we have the bits. So you break down the frame into bits, the ones and zeros, which now can be encoded. So this is how the encapsulation takes place. It is a top-down process whereby you encapsulate as you go down the model or the layers of the model, and it is going to be repeated on the end when you are de-encapsulating. So the level above does its process and passes down the segment to the level below, and that continues until the data reaches the destination. The encapsulation is the opposite. So at the receiving device, it will receive data stream zeros and ones, which have been decoded, because at this layer, data stream which is in bits of zeros and ones is going to be encoded, and we have different encoding schemes like we had said, and then it is transmitted. When it reaches the destination, the decoding takes place, the bits are gotten back, and then you start with the Ethernet frame again. It is done what? It is de-encapsulated to have the frame. Then the frame is also de-encapsulated to get the packet. Then the packet is de-encapsulated to get the segment, and then the segment to get the data. So when we are talking about data access, this is an activity which takes place at the data link and network layers. So data access is where we attach the email addresses, or not the email addresses, but the addresses depending on whether it is at the physical layer or at the data link layer, as well as the network layer. The physical and the data link layer, we are going to attach the MAC addresses, which is normally here is talking about delivering the data link frame from one network interface card to the other. So that is at the physical and the data link layer. At the network layer, we are talking about attaching the IP address, which is responsible for delivering the packet from the original source to the final destination. So this is how they are going to work. At the physical and the data link layer, we are talking about timing and synchronization bits. The data link, we are talking about destination and source physical address. At the network layer, we are talking about destination and source logical address, which is the IP. At the transport layer, we are talking about the destination and source process numbers, which we call the ports, the port addresses. And then at the upper layers after that, it is just the encoded application data, which has to be read by the specific applications. So at layer 3, we are touching the logical address, which is the source IP address and the destination IP address. This source IP address is the address of the sending device or the original source of the packet. The destination IP address is the address of the receiving device or the final destination of the packet. So they may be on the same network or the same link, or they may be remote. That has to be determined by the communication which will take place at the network. So like for example, in this picture, this is being the source which has this IP 192.168.1.110. So that IP address is a layer 3 IP address. The destination is 172.16.1.99. If you looked at the IP addressing lecture, you could notice that this is going to be a layer what? This is going to be uh, a class C IP address. This is going to be a class B IP address. So that can tell you that they are not on the same link or they are not on the same local area network. That is something just to note if you looked at that lecture, but we will come to that at a later time. So if they are on the same network, the IP addresses could have been similar, maybe on the same class, and then after that, what could be differing is the network, the host IP address. But when you look at the first or second or third octet, you can be able to tell which class of network address that is. Then the layer 3 IP address also has two parts, the network portion and the host portion, like I was telling you. The leftmost part of the address indicates the network group which the IP address is a member. And each LAN or WAN will have the same network portion. That is what I was explaining just now. Like this first octet or the leftmost part, the 192, because we said class A will start from this range to this range. We'll come back to that. Like class B, class C, D, and E. So this leftmost part should be able to tell you which class of the IP address that is. Then the remaining part of the addresses identifies the specific device within the group, and that should be the one at the end here. The host address is normally found at the end or the right hand side part. So if we come to these specific addresses, then we can see that PC1, this is the network part and this is the host part. The server, this is the network part, and this is the IP, the host part. So that can tell you that these are on the same network. Why? Because when they are on the same network, the source and the destination network part will have the same number in the network portion. So 192.168.1, 192.168.1, they are the same. The only difference is the host addresses, meaning this is host number 110, this is host number 9. So that is how you can be able to tell the difference. And these are in the same network. So if you're sending a message, it doesn't need to go outside this local area network. It will just be addressed on that local area network. So when devices are on the same Ethernet or they are in the same local area network, they will use the actual MAC addresses of the destination because the network address is the same. So they are going to be using the MAC addresses. The MAC addresses is like this, A. These are just examples, C. So these are the addresses which are going to be used for communication. These ones are physically embedded into the Ethernet card, and are local addressing. So the source MAC address will be part of the originator on the link, and the destination MAC address will always be on the same link as the source. Devices which are on a remote network, they will have some differences. Like the destination is not on the same local area network. So if this PC1, which is here, is trying to communicate with a web server, which is somewhere remote. So the local area network now is here, but as you are moving out of the local area network, which is connected through this switch, you will need to go through several routers, which are router 1 and router 2 to get to this particular web server. So this is going to have an impact on the network and data link layers because the destination and source addresses are not on the same local area network. So it means you will not be reading only the MAC addresses, but you will go to the next level where you are reading the source IP address and destination IP address. So this is what will be happening. And the role of the network layer addresses is to identify the different PCs when they are not in the same network or in the same local area network. So this is 192.168.1, that is one network. Then 172.16.1 is another network altogether. So how do you differentiate them? When the final destination is remote, layer 3 will provide layer 2 with the local default gateway IP address, also known as the router address. So the default gateway address is the router interface IP that is part of this LAN and will be the door or the gateway to all other remote locations. That is what usually happens. So our gateway will be this one, 192.168.1.1. That will be the gateway for this local area network. So you will not be using the local address here. All devices on the LAN must be told about this address or their traffic will be confined to the local area network. So even when we are configuring IP addresses, there is always the default gateway address which we normally use to get to other devices on the outside our local area network. So once layer 2 on PC1 forwards the message to the default gateway, that is the router, then the router can start the routing process of getting information to the actual destination. So once this information reaches the switch here, the switch was operating at layer 2. So the switch checked the MAC addresses and it realized that the MAC address I am looking for is not here. So what does it do? It forwards that message to the router. Now the router is going to be checking the IP addresses. So it checks the destination IP address or both the source and the destination IP addresses so that it can start now forwarding that message. So the data link is local, that is what we have said, and it will have the source and the destination, that is the MAC address. So here we are looking at the source and the destination, which is the router. Once the router receives this, the frame, then the use of local addresses ends there. Because the local addresses were used to move link to link or hop to hop. So the layer 3 addressing is still the same and it is the one which will kick in at this point. And that is where we are going now to the data link addresses and how they are going to work. So data link addresses, they will operate on the same local area network and the source in PC1, which is shown here, was AAA here, the source. The destination was 111 because it is this next device over here. So after that, what happens is that we are going to have the MAC addressing for the second hop, which is fixed. And so here it is the NIC card reading the NIC card of this router and the NIC card of this router until you get to the destination. And this is read at layer 3. So the source NIC, the destination NIC card and the source NIC card keeps on changing. If you notice here, L2 and L3, L2 and L3, meaning that you are reading both the addresses of layer 2 and layer 3. So layer 2 keeps on changing as you move from this machine to this router. So the router becomes the source as you move from here and you go to the next NIC card of the next router, it changes. And then when the router checks the destination IP address, it sees that you have not reached the destination, then it will forward to the next device. So that is how the movement occurs until you get to the destination IP address, which is the final destination. So when the web server NIC card receives the frame, then we go to the other layer, whereby the packet has not been modified, but the frame keeps on changing. Therefore, the layer 3 IP addressing does not change from segment to segment, like layer 2 MAC address. It remains the same. So the layer 3 addressing remains the same since it is global and the ultimate destination is still the web server. So that is how it works, and you get to the final destination address. So any question up to there?